Today we will see a topic, strain measurement. Strain is basically nothing but displacement or deflection measurement / deflection measurement. So, basically what we do is we try to measure strains when we are trying to apply force. We will try to see what is the deflection. It is easy to measure strain. From the strain you can try to go back and work out what is the force you applied. For example, you know the Young's modulus of a given material. Young's modulus within the elastic limits is directly proportional to stress by strain. So, what is stress? Stress is nothing but force per unit area. You know area because that is a design parameter, you know a material parameter. I measure strain, so naturally I can try to measure the force. Okay. And force measuring is not very easy, because in real time application, whenever there is a force which is acting on a body, it can be in one direction, uniaxial, it can be in biaxial, it can also be in triaxial. All the measurements what we do in the universal testing machine is on a uniaxial testing. Today slowly the concept of biaxial is also coming up. Biaxial means it is basically in two directions, the force will be applied and the strains will be measured, or the strains will be applied and the force will be measured. So, whatever it is. So, we try to do biaxial testing. Today what we talk about is triaxial testing. And when we talk about forces, the basic forces are going to be, one is tensile, the other one is compression, and the third one is going to be torsion. Okay. Torsion, and the fourth one is going to be shear. So, these are the typical forces we generally use to measure, and all the measurement is the measuring strains is very common in solid only. Gas and liquid strains are very rarely measured, gases it is very rarely measured, and solid we always go focus on it. So, when we talk about measurements, it is not only the part manufacturing and taking measurements, it is also important to measure the temperature, strains, pressure also. So, in this course we are also putting little efforts in giving you the glimpse of strain measurement. So, we will try to have the introduction for strain measurement, then LoadCell, which is a very primitive equipment which is used for measuring the strains, then MetalFoilStrainGauges, okay, then strain resistance measurement, then leads measurement, then torsional measurement, piezoelectric measurement, and floating bell measurement. So, all these things are used for measuring strains. Okay. As I told you earlier, when we talk about any measuring equipment, we try to talk about the linearity, sensitivity, okay, and the size. Of course, we would like to have passive. If not passive, we will try to have active, but in active also it has to have minimum power requirements. Okay. These are the basic things which you should always keep in mind while deciding a sensor. So, based on this we will try to choose what is required for us, and of course, cost is one thing which is very, very important. Our standards of force are ultimately based on weight magnified by a lever as necessary. Sometimes direct application of weight is convenient, like in spring balance, right, or we use a spring balance which are easily checked by attaching weight to it. So, what you measure is basically the spring. In a spring balance you try to put a mass, and moment you put a mass, the spring gets stretched. Now, how much has it stretched is nothing but your displacement. From the displacement you try to find out strain, and by the way, what is the definition for strain? Strain is nothing but dl by L, or it can be sold as dl by L. Okay. dl is the delta increase by applying the load. Okay. The minor problems with weight is the gravity varies perceptibly, mainly due to the Earth's non-spherical shape. Gravity has been measured by free falling body method to be about 9.81 Newton per kg or meter per second square in London, but would be about 9.7725 Newton per kg in Kyoto near the equator and 2800 kilometers above the sea level. You see there is a difference, that is what we are trying to say, and this difference will try to influence in the spring balance. However, they are cheap, portable and do not drift unpredictably or go out of calibration. This makes the spring balance a very common equipment for measuring strain. Now, let us see the next thing, which is called as load cell. Traditionally, platforms scales have a lever system ensuring parallel motions, so that the potential energy change for a given deflection and hence the reading is the same at all load positions. For example, this is traditional one, scales have a lever system ensuring parallel motions, so that the potential energy change for a given deflection and hence the reading is the same at all load positions. Scales using several load cells, but not parallel motion mechanism should have matched cells with equal load deflection properties and should have a highly linear output load relationship, otherwise the output will not add up correctly to all loads and load positions. So, what we are trying to say is this is the deflection and this is the load. So, we are trying to say the output should be linear. So, generally what we do is we try to have a solder which is there, then we try to have a solder joint here. So, here we have a bar or a scale, whatever it is, and then we attach two strain gauges. We will see what is strain gauge in due course of time, strain gauges, and then this is attached to a load. So, as and when you increase the weight, you can see that the deflection, the strains will increase and the deflections will be measured. Let us see now how is the load measured, resistance of load. First, let us consider a conductor having a uniform cross section of area. This is very important, AC, and length L, made of a material having electrical resistivity for this electrical conductor. For this conductor, the resistance R is given by R equal to rho E L by AC. If the conductor is subjected to normal stress along the axis of the wire, okay, then it is given reported as dr. So, the change in resistance will be dr will be AC rho E L rho E dl plus L d rho E minus rho E L d AC divided by AC square. So, here the wire. So, what are we trying to say? We are trying to say the cross section and the length change, this resulting in a change in electrical resistance R. Okay. So, the total change in R is due to several effects. So, this is what is this dr represents all about. Okay. So, this equation, I will say equation 1 can be expressed in terms of Poisson's ratio. Poisson's ratio we express because Poisson's ratio is known to us. It is a material property which is Poisson's ratio. So, we try to use it in Poisson's ratio. So, that is nothing but dr by R equal to dl by L 1 plus 2 Poisson's ratio plus dE by rho E. Okay. So, now let us try to solve a problem and see. Determine the total resistance of a copper wire having a diameter of 1 millimeter and a length of 5 centimeter. Please see, I have given one unit in millimeter, the other one in centimeter. It is good to convert it. The resistivity of a copper is 1.7 into 10 to the power minus 8 ohm meter. So, how do we solve it? So, the resistance may be calculated by R equal to rho E L by AC. Okay. So, which is nothing but AC can be expressed in terms of pi by 4 d square, which is pi by 4 into 1 into 10 to the power minus 3 the whole square, which is nothing but 7.85 into 10 to the power minus 7 meter square. Okay. Resistance is represented as R equal to 1 into 10 to the power minus 8 ohm meter into 5 into 10 to the power minus 2 meter, that divided by 7.85 into 10 to the power minus 7 meter square. So, this is nothing but 1.08 into 10 to the power minus 3 ohms. So, this is the resistance which is getting built in this problem. The resistivity of the copper is given because this is a known. See, if you see very clearly, this is a material property, this is a design or a intentionally manufactured thing. So, now using all these things, what are you trying to do is total resistance has to be measured. So, load cell is one. The next one is the metal foil strain gauges. The resistance of a strain gauge increases when put under a tensile stress, tensile compression, but predominantly we use it for tensile stress. The main reason is an intrinsic change in the material while under load, but part of the effect is the increase in length and the reduction in cross section. So, for example, you have a wire. So, when you try to pull this wire, okay, this is L. So, what happens is when you apply load, this can go to L plus delta L. When this delta L happens, so naturally the diameter, so let the diameter be D, so now the diameter will be D minus delta D. Why? Because it is a constant volume. Okay. So, the main reason is an intrinsic change in the material while under load, but part of the effect is the increase in length and the reduction in cross section. Thermal expansion is most structurally common metal exceeds 11 parts per million for each degree Celsius, whilst the gauge material could have a very different coefficient of thermal expansion. So, we talk about thermal expansion. Suppose in this shaft, if you start applying heat, if heat is applied, then what happens? What is the material property you have to take? That is what is discussed here. Since working strain may often be below 100 parts per million, it is clear that small changes of temperature could be very serious error. So, please make sure when we use this strain gauge measurement, the temperatures are not dominating. It is normally assumed that the gauge foil itself and the plastic carrier are so thin compared with the component to which they are bonded that it has a small elastic extension and same actual thermal expansion. So, let us structurally understand the use of strain gauges. So, for that we will first understand what is stress versus strain, though I gave in the introduction very brief. So, for more clarity, let us have a detailed presentation. Strain is psi is a measure of displacement usually in terms of micro strain, that means to say very small micro strain in length or diameter. Then what is stress? Stress is sigma, is a measure of load being applied on the given body where you measure the strain. Okay. So, the stress and strain are linked by modulus of elasticity E. So, Hooke's law says within the elastic limit E is equal to stress by strain, or I can say stress equal to E into strain. Okay. So, let us understand what is strain. Strain is defined as an elongation, we can say elongation in a particular direction or we can say increase in length by original length. Okay. So, these strains can be classified, there can be three different types of strains. One can be transverse strains or transverse strain. The other one can be axial strain, and of course, you have Poisson's ratio. What is Poisson's ratio? Poisson's ratio is generally referred as mu equal to sigma T by sigma A. Okay. So, then transverse is nothing but you call it as T, which is equal to change in diameter by original diameter. In axial, it is going to be A, sigma A axial. So, that is nothing but delta L by L. So, we know that increase in length or increase in diameter or Poisson's ratio has to be measured. So, now what you know? You know there is a constant volume material available with you. Once the constant material available with you expands, okay, there is a change in resistance. So, if we can measure the change in resistance, because that is easy for me to process and later use for control, because it is voltage as the output. So, I now try to measure the resistance which is getting generated or a change in resistance. So, for that what we use is we use a device called as strain gauge. So, a strain gauge is an equipment which is used to measure the change in electrical resistance, okay, of a conductor, because you can't use an insulator, of a conductor by applying load. So, if you can measure the change in electrical resistance, so that device is we use this is the basic principle for using the strain gauge or basic principle behind the strain gauge. So, the electrical resistance R can be measured by rho into L into A, where rho is the resistivity of any material, okay, which is generally given in ohm meter. A is the area, that means to say cross section area, which is always in meter square. Okay. L will be in meter, length, the unit will be in meter. So, when I find out, R will always be in ohms. If I cut down the units, place the units and cut it down, I get in ohms. So, there are some interesting facts which should know about how to increase R, or R increases with what? First is it increases with length of the conductor. Conductor is a wire, shaft, whatever it is. Okay. Next, it decreases with diameter. Okay. The other thing is it increases with temperature. Please make a note. Many a times we get erratic readings because of change in temperature, either at the conductor or when the conductor is stuck onto a shaft, where the change in temperature leads to this. And the last thing is increases with material resistivity. Okay. These are the ways and means you can change the R, or the change in R value will come based on these things. So, from there what we go is we have to now find out something called as a gauge factor. Okay. So, we know R equal to rho into L by A. Okay. So, when there is a change in R, so what we do is let us differentiate dr equal to d into P L by A plus d L by A. Okay. When there is a change in resistance, we basically start differentiating the dr. Dr is nothing but this we get. So, now when we try to expand, what happens is dr is nothing but dp L by A plus rho by A into dl plus rho into L 1 minus A square into dA. When we divide the entire thing with R, so divide equation 2 by R. So, what we get is dr by R equal to dp by P plus dl by L minus dA by A. This is what we get when there is a change in resistance. Now, we have to sort out dA. We have to find out what is dA. So, dA is nothing but where A equal to pi into d by 2 the whole square pi. Okay. So, now dA will be equal to, when you differentiate this, dA can be represented as pi 2 times d by 2 into dB, okay, or it can be dA by A, because this factor we need dA by A, which is equal to 2 times dB by B, which is nothing but 2 times epsilon, because that is Poisson's ratio. Also, we have to find out what is dl by L, which is nothing but this is axial strain, and dr by R is nothing but dP by dou P by P plus EA minus 2 times ET. This is transverse, right. So, now what we can do is, we know what is Poisson's ratio. From there we try to, because Poisson's ratio is a material property, these are design properties. So, we would like to convert this into Poisson's ratio. So, that is nothing but dr by R equal to dA 1 minus 2 times mu plus dP by P, or this can be defined as gauge factor GF, okay, that is nothing but dr by R by A, which is nothing but 1 plus 2 Poisson's ratio plus 1 by A into dP by P, and this term is almost close to 0. So, we can get gauge factor GF is equal to 1 plus 2 times Poisson's ratio. This is a factor which is very important when we start reading strain gauges. Thank you.